The symbolic approach to AI, from promise to paradox. This document explores the early symbolic approach to artificial intelligence, AI, focusing on its foundational principles, key projects, and eventual limitations. We will examine the general problem solver, the physical symbol system hypothesis, and the challenges posed by the Chinese room argument and combinatorial explosion, ultimately illustrating the shift away from purely symbolic AI towards more nuanced and data-driven approaches. The dawn of symbolic AI. In the nascent years of artificial intelligence, the symbolic approach reigned supreme. This paradigm, deeply rooted in logic and formal systems, posited that intelligence could be replicated by manipulating symbols according to predefined rules. The core idea was that by representing knowledge and reasoning processes symbolically, machines could solve problems and exhibit intelligent behavior. The general problem solver, GPS, one of the earliest and most influential projects embodying the symbolic approach was the General Problem Solver, GPS, developed by Alan Newell and Herbert Simon in the late 1950s and early 1960s. GPS was designed as a universal problem-solving machine, capable of tackling a wide range of tasks by applying a set of general-purpose heuristics. The underlying principle of GPS was means-ends analysis. This involved identifying the difference between the current state and the desired goal state, then selecting and applying operators, actions, that would reduce this difference. The process was iterative, with each application of an operator bringing the system closer to the solution. GPS was successfully applied to problems such as solving logic puzzles, playing chess, and proving mathematical theorems. However, its limitations soon became apparent. GPS struggled with problems that required significant domain-specific knowledge or that involved a large search space. Its reliance on predefined rules and its inability to learn from experience hindered its scalability and adaptability. The physical symbol system hypothesis. The symbolic approach was further solidified by the physical symbol system hypothesis, also proposed by Newell and Simon. This hypothesis stated that a physical symbol system has the necessary and sufficient means for general intelligent action. In other words, any system that can manipulate symbols according to rules can, in principle, exhibit intelligence. A physical symbol system, according to Newell and Simon, consists of symbols, physical patterns that can be combined to form symbol structures. Symbol structures, collections of symbols that represent knowledge or information. Processes, operations that manipulate symbol structures. Rules, instructions that specify how processes should be applied to symbol structures. The physical symbol system hypothesis provided a theoretical foundation for the symbolic approach to AI. It suggested that intelligence was not tied to any particular biological substrate but could be realized in any physical system capable of manipulating symbols. This idea fueled much of the early research in AI and led to the development of various symbolic AI systems. The Chinese room argument. Despite the initial successes and theoretical appeal of the symbolic approach, it faced significant challenges. One of the most influential critiques came from philosopher John Searle, who proposed the Chinese room argument in 1980. The Chinese room argument is a thought experiment designed to challenge the claim that a machine can truly understand or be intelligent simply by manipulating symbols. Imagine a person who does not understand Chinese is locked in a room. This person receives written questions in Chinese and, following a detailed set of rules, manipulates symbols to produce appropriate answers in Chinese. To an outside observer, it might appear that the room understands Chinese. However, Searle argued that the person inside the room does not actually understand Chinese. They are simply manipulating symbols according to rules, without any comprehension of the meaning of those symbols. Similarly, Searle argued that a computer, even one that can pass the Turing test, does not necessarily understand or be intelligent. It is merely manipulating symbols according to its programming. The Chinese room argument raised fundamental questions about the nature of understanding and intelligence. It suggested that simply manipulating symbols, even in a way that mimics intelligent behavior, is not sufficient for true understanding. This critique challenged the core assumption of the symbolic approach to AI and prompted researchers to reconsider the role of meaning and consciousness in artificial intelligence. Combinatorial explosion. Another significant challenge facing the symbolic approach was the problem of combinatorial explosion. As AI systems attempted to tackle more complex problems, the number of possible symbol combinations and rules grew exponentially. This led to a situation where the search space became too large to explore exhaustively, making it difficult to find optimal solutions. For example, consider a chess-playing program based on the symbolic approach. The program would need to represent the board state, the possible moves, and the rules of the game symbolically. As the game progresses, the number of possible board states and moves increases dramatically. The program would need to evaluate a vast number of possible move sequences to determine the best course of action. The combinatorial explosion problem highlighted the limitations of the symbolic approach in dealing with complex, real-world problems. It became clear that simply adding more rules and symbols was not a sustainable solution. More efficient search algorithms and knowledge representation techniques were needed to overcome this challenge. The shift away from purely symbolic AI, the challenges posed by the Chinese room argument and combinatorial explosion, along with the limitations of systems like GPS, led to a shift away from purely symbolic AI towards more nuanced and data-driven approaches. Researchers began to explore alternative paradigms, such as connectionism. This approach focuses on building artificial neural networks that mimic the structure and function of the human brain. Connectionist systems learn from data by adjusting the connections between artificial neurons. Statistical AI. This approach uses statistical methods to analyze large datasets and extract patterns and relationships. Statistical AI systems can learn from data without being explicitly programmed with rules. Embodied AI. This approach emphasizes the importance of embodiment and interaction with the environment in the development of intelligence. Embodied AI systems are typically robots that learn by interacting with the physical world. These alternative approaches have achieved significant successes in areas such as image recognition, natural language processing, and robotics. While the symbolic approach still has its place in certain specialized applications, it is no longer the dominant paradigm in AI research. Conclusion: the symbolic approach to AI, with its emphasis on logic, rules, and symbol manipulation, played a crucial role in the early development of the field. Projects like the General Problem Solver demonstrated the potential of symbolic AI, and the physical symbol system hypothesis provided a theoretical foundation for the approach. However, the challenges posed by the Chinese room argument and combinatorial explosion, along with the limitations of symbolic AI systems in dealing with complex, real-world problems, led to a shift towards more nuanced and data-driven approaches. While the symbolic approach may not be the dominant paradigm today, its legacy continues to influence AI research, and its insights remain relevant in the ongoing quest to understand and replicate intelligence.